Hey everybody, this is the second video in our series of videos for Unit 5 on probability. This video is basic probability rules. So some of these things you may have seen before or heard before, but I want to make sure that I talk about all of them because it's the foundation of everything we do with probability. Okay, so whenever we're talking about probability or calculating a probability, really what we're looking at is something called a probability model. Okay, because oftentimes we're just looking at the numbers. We're like modeling the data. We're not necessarily like, looking at the actual people that were involved or the actual, things that were involved, right? Okay, so a probability model has two things. It contains something called a sample space, which is the set of all possible outcomes. Okay, and it also contains a probability for each outcome. Okay, right? And then an event is something that we want to know the probability for, essentially, right? So an event is any collection of outcomes, okay? And it's always designated with a capital letter. Okay, so the example that I have on the screen here is rolling 2 dice, okay? So the sample space has 36 possible outcomes, right? Because you could roll a 1 and 1, 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, and then that would repeat for the first number changing, right? So 36 possible outcomes because there's 36 possible combinations of the 2 dice. Because these are fair dice, each outcome, meaning like 1 and 1 and 2, 1 and 3. Each of those is an outcome. Each of those outcomes is equally likely with a probability of 1 out of 36. Okay? If the event that we are concerned with is, I want to know what's the probability that I roll a sum of 5. Okay? There's 4 possible combinations that give us a sum of 5, right? 1 and 4, 2 and 3, 3 and 2, and 4 and 1, right? So 4 outcomes out of the possible sample space of 36. So that probability is 1 out of 9. Okay, so that's some basics about probability models. Okay, and then there's a couple of key like foundation probability rules and definitions that we need to know. So the first is this term mutually exclusive, or you may hear events called disjoint. Okay, so events are mutually exclusive if they have no outcomes in common and can never occur together. So two events that have no outcomes in common and can never occur together. Okay, so a common example you'll hear people use is talking about playing cards, right? So it's not possible for me to pull one playing card that is both a red card and a black card at the same time. Those two events are mutually exclusive or disjoint. Okay, the way that we notate that with probability notation is we would say the probability of A and B, meaning both of those events occurring together, equals 0. Okay, another very, very important term is this term complement, okay, which means essentially it means not, right? So a complement is the probability of an event not occurring. Okay, and it's noted with a subscript C, and I know it's not written on here, but it's also notated with prime notation. So meaning if I have an event A, the complement would be A prime, right? So if you see, or it's written like this, A, C, right? So each of these little notations here literally translates to the word not. Okay, so that's kind of what you want to think when you are when you're thinking about complements, right? The key phrase that you want here is the word not. Okay, right? And then just as a reminder, right, the way that we calculate probability, okay, is the number of outcomes for the event that we're looking for divided by the total number of outcomes in the sample space. Okay, and then my complement rule, which is very important to remember, okay, is that you can find the probability of something not happening by doing 1 minus the probability of that event actually happening. Okay, right? Because for any event, if you boil it down to its simplest terms, you only have two options. Either the event happens, which is this probability of A, right? Either the event happens, probability of A, or it does not happen, which is this probability of A complement, right? And those two values together, probability of something happening plus the probability of it not happening, encompasses all possible outcomes, right? All possible values. So they would add up to equal 1 or 100%. Okay. So if you want to find the probability of something not happening, subtract the probability of that thing happening from 1. Really similar to what we did when we did normal distributions. And remember when we were trying to find a probability shaded to the right, we would do 1 minus the probability shaded to the left in the z table, right? Okay, so let's look at some practice problems here, because genuinely the best way to do probability problems is to just jump in and like write some fractions. Okay, so I have this data set here where we have a group of freshmen, sophomores, juniors, and seniors in a school, right? And we ask them to pick a color from these three colors: red, blue, green. Okay, so what you'll see here, this first question is, what's the probability that a randomly selected student voted green, right? So if I look here, my total number of greens is 397 divided by the total in the table, which is 2,500. Okay, so it genuinely is that simple. Okay, but there are a couple of things that you have to indicate when you answer these problems. The first is that probability notation. Okay, so I have to write probability of green equals, and then you can write your fraction, 397 divided by 2,500. Okay, and then I went ahead and figured out what that decimal is, 1588. Okay, usually it's a good idea to figure out what the decimal is, but it would be okay if you didn't, right? Like you could just answer this with the fraction, right? But the reason that this is so important, right, is because this right here is your context. Remember, statistics is all about context. Okay, if you just say, and you just give this blank answer, like 0.1588, or just this blank answer, 397 over 2,500, it has no meaning. That number has no meaning, no context, right? So you have to use the probability notation so that the AP readers know what you're talking about. Like they know that that's what you're finding, right? And you're able to put this in context. Okay. All right. So the next question here is, what's the probability that a randomly selected student did not vote green? Okay. Now, there's two ways that I could do this, right? I could say, well, not green means either red or blue. So I could add those together and divide by the total, right? But wouldn't it be much easier to just do 1 minus the probability that that event did occur? Because we already calculated it, right? So that would be much easier, right? So when you're writing this out, this is, so the probability of not green, and I'm typing, so I'm writing the word not out, but you can use the complement notation. That's fine. So that equals 1 minus 0.1588, which is 0.8412. Okay, and 2 is the complement of 1. Okay. All right. Right. So there's my answer there. Right. Green and not green are complements. Okay. 4 says, what's the probability that a randomly selected student is a senior, right? So rather than looking in these margins, right, the ones down here at the bottom, I'm going to look in the column margins here, right, which is 600, right? 600 seniors divided by the total, 2,500. So if I'm going to put that in probability notation, that's P parentheses senior. I found the probability of senior, which is 600 divided by 2,500. And then if you want to give that or put that in decimal form, it's 0.24. Okay. Okay. So that's just some like basic calculating probability from a two-way table. Okay. Now, this next question asks, what's the probability that a randomly selected student voted blue or is a junior? Now, the word or is, it means something different in the English language than it does in probability terms, okay? In the English language, when you hear the word or, you usually think, well, I'm going to do either this or this, but I won't do both, right? In probability, or means falling in one category, falling in the other category, or falling in both categories, right? So if I'm talking about blue or junior, sorry guys, I've lost my thing here. Okay, so blue or is a junior means that that person could have a favorite color of blue, they could be a junior, or they could fall in both of those categories. Okay, so there are a couple of ways that you could look at this, right? So I could take and look at my two-way table and say, okay, which is what you see here on the slide. So I could say, okay, there's 1,200 students that selected blue. Okay, and then I just have to think, okay, who haven't I covered, right? So I haven't covered the juniors that chose other colors, right? Because I have the juniors that chose blue and all of the other people that chose blue, but I haven't covered the juniors who chose the other colors, right? Which is 216 and 83. So you would add all of those together, right? And divide by the total in the two-way table, right? So you can do 1,200 plus 216 plus 83 and do that whole thing divided by 2,500. Okay, and what that'll give you is 1,499 over 2,500. Okay, so that's one way that you could do this. Or there's another way, which I personally think is a little bit more efficient, because it will work no matter how big your two-way table is or how many like instances in each category that you have, right? It was fairly easy to do the problem this way just by adding the individual cells when we didn't have a bunch of cells to work with. But let's say these colors had more than just red, blue, and green. Let's say it had all the colors in the rainbow plus a couple more, right? It would have been a big pain for me to go, okay, 1,200 for blue, and then I have to add all of the other categories, red, green, yellow, purple, pink, cyan, right? It would go on and on and on and on. So I personally think it's easier to calculate OR probabilities this way, Okay, so you find the total in the first category. Right, so the total for blue was 1,200. The total in the second category for junior, so that's 575. And then you have to subtract the number that they have in common. Okay? Okay, here's why. If you just add the 1,200 and the 575, you have counted these people twice. You counted them once when you added all the juniors together, and you counted them twice when you added all the blues together, right? So we don't want those people to be counted twice. So we have to subtract one of them out, okay? So the way that you would then write this is 1,200 plus 575 minus 276. All of that, again, still divided by 2,500. Okay, and you're going to get the exact same thing, 1,499 over 2,500. Exactly the same thing. Okay. All right. Okay. So let's look at number 6, okay, which says find just the probability of voting blue plus the probability of junior, right? And they want to know why is that different from the answer in number 5, okay? So probability of blue is 1,200 divided by 2,500, okay, plus probability of junior is 575 divided by 2,500, right? So when you add all of that up, right, you get, and I'm just adding the decimals here, but you get 0.71, which is different from what this value was up here in the previous question, right? That probability, which I didn't write, but I did show on the screen briefly, was 0.5996. Okay, so those probabilities are different, right? And the reason for that is that 276 juniors who voted blue were counted twice. Okay. So it's essentially what I just talked about, right? So what I'm going to do here is I want you to try on your notes 7, 8, and 9, okay? Because it follows the same pattern, right? But I want you to try those out and see if you can figure those out. I'm also going to fill them in. So pause the video, try 7, 8, and 9, and then check back with me to see if you got the answer right. All right, folks, so if you went ahead and solved this on your own, you should have gotten the exact same probability for both 7 and 8. Okay, and the reason that that happened is because these two events have no students in common, right? That their joint probability, their and probability would be 0 here because there were 0 freshmen that had green as their favorite color. Okay, so what that means is that these two events are mutually exclusive, or you have heard me call them disjoint. Okay, so all of that together comes to one of the most important foundational rules in probability, which is called the addition rule. Okay, so the way that you use the addition rule is it gives us a relationship between or probabilities and probabilities, so unions and intersections. So if I'm finding the probability of A or B occurring, right, event A or event B, I'm going to add the sum of the individual events, probability of A plus the probability of B, minus the probability of A and B. Okay, keeping in mind that A and B here is what those two events have in common, right? It's whoever is counted twice. Okay, and then I have a lovely little table for you that has all of your symbols in it. Okay, so the word and in probability is called an intersection. Okay, and it's represented with this little upside down U, okay, which to me looks like an A just without the line in the middle. So that's how I remember it. Okay, so the way that this is written in actual probability notation is probability of A and B. So rather having to write the word and, you could just write this symbol, right? It literally means, this symbol literally means or translates to the word and, okay? Or is called a union, okay? And it is represented with the opposite symbol, with a big capital U looking symbol, okay? So an equation or example here is the probability of A union B. So if you see something that looks like that, this little union symbol, the upside down U, literally translates to the word or. All right, so that is it for this video. In the next video, I'm going to talk about conditional probability and independence. It's another very, very important foundational rule for probability. It comes up all the time on the AP test. They love to use conditional probability and Bayes' theorem and all of that fun stuff. All right, so I will see you in the next video. Bye, everybody.